And as Virginia has said, I'm going to talk about two very classical problems, the Dirichlet problem and the Neumann problem. And we are going to deal with some questions about the endpoint, what happened at the endpoint. I will explain you in a moment. And this is a joint work with Virginia and Carmen Ortiz Caraballo. So let us start by putting the things in the context. Everything that I'm going to talk is in the 2 dimensions. So we are going to work in the complex plane. And we are going to work in a Lipschitz domain, which is defined as it is here. And this means that we are going to take the x plus iy, and the variable y is bigger than nu of x, and nu is the Lipschitz function. So we want to examine some new aspect of the Dirichlet problem, which consists in finding a harmonic function in the domain, so that at the boundary, u restricted to the boundary is equal to the data function f. And we have to say, what does it mean, this equality? Initially, the function f is continuous just for everything to be well defined, but then we don't need that much regularity. So we could say that the Dirichlet problem is LP solvable if for every function f in LP, we can find a harmonic function in such a way that when we take the supremum over the variable y of u, x plus iy, this is a bounded operator from LP into LP. That in particular implies that we have almost everywhere convergence at almost every point. Okay. Now we are going to assume something more. We are going to ask for something more because we want to have not only convergence at almost every point vertically, but non-tangentially. So to this end, we have to consider the so-called non-tangential maximal operator. So we just have to take the supremum of the function u of c, where c belongs to the cone with vertex at the point c. Okay, and the cone, we have here the definition, where alpha is the aperture of the cone. Okay. So if we want to have almost everywhere convergent non-tangential, so inside the cone, the definition that we are going to give is that we say that the Dirichlet problem is LP solvable for p bigger than 1 if for every function f in the space LP, we can find a harmonic function in such a way that the operator M alpha is bounded from LP into LP. So this is going to be our definition. And here we have to assume that p is bigger than 1, because if p is equal to 1, this never happened. Okay, but well, okay, so first of all, let me just say that, as I said before, if we have the boundedness, then automatically we will have the almost everywhere convergent at almost every point. So as I said, for p equals 1, we cannot assume a strong type. So the operator, we cannot impose that it has to be from L1 into L1, because this never happened. So we have to change the definition and say that the Dirichlet problem is solvable in L1 if the maximal operator takes L1 into a bigger space than L1, which is the weak L1 space, L1 infinity. And well, this is a perfect definition, because in fact, this weak type boundedness also imply the almost everywhere conversion. Okay, so that's okay. So our starting motivation of the problem that I'm going to explain is the following theorem due to Carlos Kenny in the 80s. He proved that for every Lipschitz domain, there exists a P0 less than 2, so that for every P strictly bigger than P0, the Dirichlet problem is solvable. And moreover, if P0 is bigger than 1, the result is false for every P less than or equal than P0. Okay. Now, well, let me tell you some previous result to this theorem of Carlos Koenig. First of all, Fabes, Jodait, and Riviere studied the case of a bounded Lipschitz domain where the boundary was C1 regularity. And they proved that in that case, P0 is equal 1. In the case of unbounded domain, Carlos Koenig proved that the C1 boundary regularity was not enough to have P0 equals 1. So they need some more conditions. And then also there are some results of Dalbert for dimension m bigger or equal than 3, that he studied the case of bounded Lipschitz domain. Okay, so as I said at the beginning, we want to present some new aspect of these two very classical theorems, and this new aspect concern the endpoint P0. So the two questions that we want to solve, well, the main one is the first one, okay? So the question that we want to solve, it is the following. We know that the Dirichlet problem is not solvable in LP0 if P0 is bigger than 1. So we want to prove if we can find some space X contained in LP0 in such a way that the Dirichlet problem, it is solvable in the space X. And the second question is, okay, where this P0 come from? How can we compute it for some domain? So to attack this problem, we are going to start from the very beginning, which means that we are going to start by solving the Dirichlet problem in the upper half space, which is something that the students study, and it is easy to understand. Okay, so the situation is we have a function f, which initially we are going to assume that it is very good, and then we consider this function here, which is the Poisson kernel, which is harmonic. And therefore, if we consider the convolution operator of the Poisson kernel with the function, then this function is going to be harmonic. And the point is that if we consider the maximal operator, here I have written the case where we are only interested in vertical convergence. So let's say the supremum of in y bigger than 0. Then this operator is bounded from LP into LP, and it is bounded from L1 into weak L1. But moreover, if we consider the case, as I said before, of the non-tangential maximal operator, then it is also true that this operator is bounded from LP into LP and from L1 to weak L1. Therefore, what we are saying here is that in the upper half space, this is the solution that we are looking for. Now we want to pass to a Lipschitz domain, and Lipschitz domain are simply connected, and therefore we have the Riemann mapping theorem that says that it is conformally equivalent to the upper half space. Okay, so this is the scheme that Carlos Koenig did in his paper. So the idea is that we have a function here defined on the boundary of the Lipschitz domain. Then we can compose the function with the conformal mapping. Then we have come into a context where we know where to solve the problem. So we have here the Poisson kernel. We can consider the harmonic function, and then since this function is analytic, we can compose with the inverse, and the function B is going to be the solution. So this is the scheme of the proof of Carlos Koenig. Now, what is the point? The first point is that if we have a function here in LP, then the function f composed with phi is not in LP anymore, because of course we have chain of variable and it is in LP of a weight. This is going to be a integrable, locally integrable function positive. So this is called a weight. And of course it is an isometry. So what we need is to solve the problem in the upper half space, but not for LP, as I have done before, but for LP with an absolutely continuous measure which come from the Jacobian of the chain of variables. So how to do that? So, well, initially we are going to take the same function as before because it is a very nice harmonic function. And what we need to answer is if the maximal operator, the non-tangential maximal operator, takes LP of that weight into LP of that weight. If this happens, then we have solved the Dirichlet problem in the Lipschitz domain. Now, it turns out that this non-tangential maximal operator, it is bounded from above and from below by the hard-deletable maximal operator, which I have written here, the definition, right? So the question that we have to solve is if it is true that the maximal operator is bounded on the space LP of the Jacobian. So we have to answer this question for which weights the maximal operator is bounded. Now, it turns out this was what I explained at this moment it is what it is in the paper of Carlos Kenny. Now, it turns out that this problem had been solved some years before by Mackenhaupt and in other contests. Okay, there are many different contests where this problem is really very important. And the answer is that the maximal operator is bounded on LP if and only if the weight is in the nowadays called Mackenhaupt class, which is the definition I have written here, the definition, well, for completeness, okay? But the definition is not going to be important for our purposes. The main point is that Mackenhaupt completely characterized the boundedness, the weights omega for which the maximal operator is bounded on LP of omega. And this goes for P bigger than 1, and for P equals 1, it is also completely characterized, and the condition is called that the weight is in the A1 class, which is the definition it is here. Okay, so this problem is completely solved. And what was the main point or the technical part, or I think that it is the core of the paper of Carlos Kenny, is that he proves that if you have a Lipschitz domain and you take the conformal mapping, then the Jacobian is in the class of A2 of Mackenhaupt. Okay, so this is, let's say, the technical part of the theorem of that paper that I mentioned before. And therefore, we have that the maximal operator is bounded from L2 into L2. And as a consequence, for every Lipschitz domain, we have that corollary that for every Lipschitz domain, the Dirichlet problem is solvable in L2. Now, it turns out, and this is a very easy property, just as a consequence of Hölder's inequality, that this class is increasing. So if P is less than or equal than Q, AP is contained in AQ. So the Jacobian is in AP for every P bigger or equal than 2, and therefore the maximal operator is bounded on LP of Phi prime for every P bigger or equal than 2. So the corollary is that for every Lipschitz domain, the Dirichlet problem is solvable in LP for every P bigger or equal than 2. Now, if you remember the motivation theorem that I had given you at the beginning, it said the RC is a P0 less than 2, so that the Dirichlet problem is solvable for P bigger than P0. Okay, so where this P0 comes from? This P0 comes from a very important property of this class of weights that says that if you have a function in AP, there is an epsilon, of course, depending on the weight, in such a way that omega is in AP minus epsilon. Okay, so now we understand why there is this P0 that depends on the Jacobian, and therefore it depends on the domain, so that the Dirichlet problem is solvable for every P bigger than P0. Now, the second part of the theorem says the result is false for LP0 if P0 is bigger than 1. And this is clearly because what it is that P0? P0 is exactly the infimum of the P so that phi prime is in AP. And of course, since that property is open, omega, if P0 is bigger than 1, omega cannot be in AP0, because if not, it will be an epsilon, and it will be in AP0 minus epsilon. And that's the reason why the result is, the Dirichlet problem is not solvable in LP0. Okay, so let me give you two examples of the Lipschitz domain. So if the Lipschitz domain is given by a cone of aperture alpha, and this alpha is less than or equal than 1, then it's very easy to compute the Jacobian, and therefore it is very easy to see that the Jacobian is a weight in A1, and therefore in this domain the Dirichlet problem is solvable in L1, and of course in LP for every P bigger or equal than 1. However, if the domain is the aperture of this cone alpha is bigger strictly than 1 and less than 2, then it happens that phi prime is in a P if and only if P is bigger than alpha, and therefore the P0 is exactly equals to alpha. And according to Carlos Kenny's theorem, this in this domain that we have here, the Dirichlet problem is not solvable in L alpha. Okay, so the reason, so what we have is that the reason because the problem is not solvable in L alpha is because M alpha is not bounded from LP0 of phi prime into LP0 of phi prime. Okay. Now, when we have an operator that it is not bounding from LP0 into LP0, and we are looking for some boundedness, we have, well, there are many possibilities, but I'm going to talk about two paths. Okay, so one path goes for what is called Lorentz spaces, which means that instead of looking for the boundedness on LP0, we may try to see if the operator is bounded from what is called restricted weak type boundedness, which means that we want to study if the operator is bounded from LP01 into LP0 infinity of phi prime. Well, these spaces will appear later, but let me just say that LP01 is smaller than LP0, and LP0 infinity is bigger than LP0. So this condition is weaker, and therefore we may have some hope that for some domain we may have restricted weak type. And the second path is by logarithm. Okay, so let me say Orlich spaces. And this second path is based in the following thing. We know that M alpha is bounded from LP of phi prime into LP of phi prime for every P bigger than P0. This is what we have said before. But it is not bounded, from LP0. So if this happens, it means that the norm of M alpha on that space has to blow up to infinity when P goes to P0. Okay, and then we will see that if we have some information of how this blows, how this behaves, then we still have some opportunity to have some boundedness in some logarithm spaces. Okay, so this is what we are going to do now. So we are going to start by the case of Lorentz spaces. So as I said before, here we have the definition of Lorentz spaces. So these spaces we can define either using the distribution function. So this is the measure of the level set, what the function f is bigger than y. Or if you are familiar with the decreasing rearrangement, we also have, because these are rearrangement invariant spaces, and we also have the definition with the function, with the decreasing rearrangement function. But if you are not familiar with those spaces, it is okay, just you only have to know as I said before, that the space LP1 is smaller than LP, and LP is smaller, strictly smaller than the weak LP. Okay, so we can give the following definition. We say that the Dirichlet problem is solvable in the space LP1 if there exists a harmonic function satisfying that this operator takes LP1 into LP infinity. So if we want to solve the problem in the space LP1, which is what we are going to, okay, so let me just give you before general definition for an arbitrary space X. Okay, so the Dirichlet problem, we are going to say that it is solvable in some space X if there exists a harmonic function and a reasonable space Y in such a way that the operator takes the function is bounded from X into Y. Okay, so what it means reasonable? Reasonable means just that if we have the boundedness, then we have the almost everywhere convergence. So in that we are going to give this general definition, because as you will see, not all, when we try to solve the problem, the Dirichlet problem in LP, the boundedness is from LP into LP. But if we go to some other spaces, maybe the boundedness from X to X, it cannot happen, as I told you before, for the case P equals 1, and there are many other situations where the maximal operator goes from some space X into some space Y, but if we have that condition, then we say that that space is reasonable. Okay, so let us try and see if we can solve the Dirichlet problem in the smaller space LP01. So to this end, we need to study the boundedness of the maximal operator from LP1 into weak LP. Okay, and this boundedness was already known in '82 by Kerman and Torchinsky, and they completely characterize the weights for which this boundedness happens. Okay, and this class is called restricted AP class. I will define it in a moment. So now the important thing is that this class is bigger, of course, than the class AP. Okay, so maybe a weight is not in AP, but it might be in APR. Okay. So let us see in the two examples that in the example that I have given you before, when alpha was when the aperture was bigger strictly than 1, then we say that the Dirichlet problem is not solvable in L alpha because the phi prime is not in A alpha, but it turns out that it is in the restricted class A alpha R. And therefore, since this happens, we can say that the Dirichlet problem in this domain here is solvable in the Lorentz space L alpha 1. Okay, so let us talk a little about this class APR. This class APR is defined in the following way. Okay, so we have here. So the situation is that we have here remember we have here the upper half space, we have here the function phi, and then we have here the domain. And then what this definition says that if we take y is any interval, we take y an interval, and we have here the image of the interval. So this is phi of y. And then we take here any measurable set inside. So this is E. And we have something here, which is phi of E. Okay, so this class of weight needs that the measure of phi of y divided by phi of E has to be controlled in this way by the measure of y divided by E. Okay, if we just pass, oh, sorry, if we just pass this to this part. Okay, so this means that we can define this function here. So for every t bigger than 1, we can define the function phi of t, like the supremum of this quotient, where the supremum is taken over all measurable set contained in an interval, and this is the supremum for every interval, under the condition that the measure of the interval is equal t measure of E. And this condition here says that a function, that the weight phi prime is in APR if and only if this function here is bounded by the power t to the p. Okay, so this is another way of looking at the definition of APR. Now the point is that this is one can check that this function satisfies that it is submultiplicative in this sense. Okay, and using the submultiplicative property, it turns out that that a weight is in APR, but not in AP, in AP0R, but not in AP0, if and only if this function is equivalent to t to the power p0. And therefore, this function phi bar gives us a way of computing exactly the value of AP0 by that formula that I have written here. Okay, so as I said before, this class APR is bigger than AP0, but it is not that much bigger because in fact it's contained in AP for every p bigger than p0. So it is between AP0 and AP for every p bigger than p0. Now we know, we have said before, that given p0, u is never in AP0. So the point, the question that we ask is, okay, is it always true that the u is in AP0R? If this, if the answer to this question is positive, then we can say that the Dirichlet problem is always solvable in LP01, okay, in the Lorentz space LP01. However, the answer is no, because we managed to construct this weight, and it turns out that with the computation that I have given you before, we check that the P0 is R, and that the function phi bar is not equivalent to t to the r, so the weight is not in restrictive weight type. Okay, so this is for general weight, but the point is that initially our weight were not general, right? Because they are the Jacobian of the conformal map. So we said, okay, maybe if it is the Jacobian of a conformal map, we have a positive answer. But the question, the answer is also again negative, because Carlos Kenny proved that there is a bijection. Given any weight in A2, there is always a Lipschitz domain, so that U is precisely the Jacobian of the conformal mapping. Okay, so the point is that no, it is not true that the Dirichlet problem is always solvable in LP01. It is for some cases, as the one that I have showed you before, but it is not always true. And then we try to go through the second path, which is the solvability in logarithmic spaces. So let me, we are going to motivate what we are going to do with this example, because as I said, if we take the Lipschitz domain with this Jacobian, then the Dirichlet problem is not solvable in LR1 because it is not here. But it happens that if we compute the norm in AP for P bigger than R, it can be checked that the norm behaves like 1 over P minus R to a certain power R minus 1. Okay, and in fact, there are many cases in which weights are not in AP0 R, but there is some information about the behavior of the norm of the weight in APR when P goes to P0. And this connected, okay, so we are going to solve two cases because they are different. One is the case P0 equals 1. So the situation is going to be that we have some weight which is not in A1, but it is in APR, and the behavior is like 1 over P minus 1 to the n. And the second case is similar, but for P0 bigger than 1. Okay, let me just say that we can assume here a different decay. I mean, or growing, it depends, all right? Because this is going to go to infinity. But when we have this decay, this make a connection with a very classical theorem, an old theorem, because it's due to Llano in the 50s, that tell us the following. If we have a sublinear operator and our operator, our principal operator is the maximal, the hard-derivative maximal operator. So we have a sublinear operator, and we know that it is bounded from LP into LP with that behavior of the constant. Then Llano proved that that operator takes the space L log L to the M into, well, in fact, he proved into L1 because he was working with a finite measure, okay? But their proof is easy modified. And if the measure is not finite, which is going to be our case, then it takes L log L to the M into the space L1 plus L infinity. And you have here the definition of the space L log L, which is nothing but instead of having integrability, we need to put here some extra logarithm integrability, okay? Now, in 2004, in a joint work with my colleague at the University Autónoma of Barcelona, Joaquim Martín, we extend a little Llano's theorem in the following way. First of all, we were interested in assuming restrictive with type with that behavior of the constant. And then what we obtained was that instead of arriving to L log L, we have to add this log 3. So it is the logarithm of the logarithm of the logarithm integrability, okay? Now, the reason why this part here appears is because when P goes to 1, the space LP infinity goes to weak L1, and weak L1 is not a Banach space. And that's the reason why we have here this log 3, okay? Now, for our purpose, this was not a good result because it turns out that that space is not a reasonable space because of this part of L infinity. But in fact, this theorem, we also improved it a little, and we found that, that in fact it arrives to some reasonable space, and therefore this is the theorem that we can apply for our purposes. So the question that we need, okay, sorry, we need to study. We know that the boundedness of this operator holds if the weight is in APR, but we need to know how is the norm of this operator in order to study how is the control. Now, this kind of result is what we call SARP constant, or for constant for the hard-derivative maximal operator, and this was studied by Bagley in '93, where he proved these two results. He proves that the norm of the maximal operator on LP of omega behaves in this way. And let me tell you that this is a very bad constant for Llano's extrapolation theory, because this is okay, but this is very bad. Okay, because this blows up in a very bad way. But in the case that instead of a strong type, we have weak type, then the constant is very good. And also in the case of restrictive weak type, which is the case that we are working with, the constant is also very good. Okay, so this is the result. This is precisely the result that we can use. And the conclusion is that if we are in the case where the Jacobian is not an A1 weight, but we know that behavior of the constant, then the non-tangential maximal operator satisfies exactly the hypothesis of the previous result. And as a consequence, we know that it is going to be bounded from the logarithm space, from this logarithm space, into a reasonable space Y. And the corollary is that under that situation, the Dirichlet problem is solvable. It's not solvable in L1, I insist, okay? So because of that, it is not solvable in L1, but it is solvable if we add some extra integrability in the function. And similarly, for the case P0 bigger than 1, with my colleague Joaquin Martin, we extended the result, the Janos extrapolation result, to this situation where P goes to P0. And then we find out that yes, the operator takes some space, which I'm going to define in a moment, into some reasonable space. And what it is the space X? This space X is not enough to have that the function is in LP01. So remember that well, if you don't remember, I'm going to tell you in a moment. The norm of a function in LP01 is exactly this quantity when we put here an infinity, okay? So this is the norm in LP01. But this, to be that this quantity is finite is not enough, but we need some extra condition, and it is that when t goes to 0, this thing has to go to 0 to a speed sufficiently fast in order to have integrability with respect to that not so good function, right? So this is the condition that we need to impose to have that the operator is bounded from X into some reasonable space. And therefore, in the case that the phi prime is not, we are in the case that phi prime is not in AP0, I will say, the Dirichlet problem is not solvable in LP0. If the Jacobian is not in AP0R, is not solvable in LP01, but there is still some hope that we can have boundedness in this space as the Dirichlet problem is solvable in this space, logarithm type space, okay? And in particular, this is what happened with the example that I have given to you before, okay? For that, for the Lipschitz domain corresponding to that case, it is not solvable in R, it is not solvable in LR1, but we have managed to find the right integrability condition to have that the Dirichlet problem is solvable in that space. Okay, so this is what I wanted to tell you concerning the Dirichlet problem, and now we have to deal with the Neumann problem. So let me just say that to study the Neumann problem you will see that the context or the methodology is going to be the same, right? But the amount of technical problems that we have found, I mean, this problem has been much more difficult than the Dirichlet problem. Okay, so I'm going to try to explain you why this Neumann problem has been for us much more complicated. Okay, so let us just define what it is the definition. We say that the Neumann problem is solvable in some space X if there exists a reasonable space Y, so that for every function in X, we can find a harmonic function on the domain, so that the normal derivative where n is the outer normal vector, is coincide with the function f on the boundary, and we need to have a control of the gradient of the function. Okay, so now we have to have some boundedness, but instead of having here the function b, we need to have the control on the gradient of the function. And this is the second theorem that was the motivation for us to study the situation at the endpoint. And it is also, this theorem is also due to Carlos Koenig. So let's say they prove that for every Lipschitz domain, there is now Q0 is bigger than 2, so that for every P between 1 and Q0, the Neumann problem is solvable in LP. Okay, so this is the theorems, and let me tell you a little of the story. First of all, Fabes, Jodait, and Riviere also studied this problem for bounded Lipschitz domain with C1 boundary. and then the dimension n bigger or equal than 3, and they proved that Q0 was infinity. Then after Jerison and Kenny study also the case for bounded Lipschitz domain without regularity, and they proved the solvability in L2. After that, Dalbert and Kenny improved the result of Jerison and Kenny. They studied the case of bounded Lipschitz domain and for dimension n bigger or equal than 3, and they solved it for P between 1 and Q0 bigger than 2. And then there are other papers, and in fact, the only paper where they do something for n equals 2 is due to Fapes and Koenig, but it is in an unpublished publication that we couldn't find. In fact, we knew about that because it is mentioned in this paper of Jerison and Koenig, and then we found some information in some paper in some proceedings where they state the result and give us some ideas. Okay, so to solve the problem at Q0, we need to first understand the problem for P less than Q0. Okay, so let us start again with the half space. So this is the situation. Since we want that the normal derivative in the upper half space is the derivative with respect to the second variable, and we want that this is the one that, let's say, converges very well to the function f, it is natural to consider that this is going to correspond to the convolution with the Poisson kernel. Okay, this minus comes because the vector is the outer vector. And then to have that, what we have to consider is this harmonic function, which is the convolution with the fundamental solution of the Laplace. And in that case, since we also need to control the gradients, we also need to control the derivative with respect to the variable, with the first variable. And it turns out that if we do the computation, what we have here is the conjugate of the Poisson kernel. Okay, so this Poisson kernel mass I times the conjugate is an analytic function. So we need to control the maximal operator of both the derivative with respect to the two variables. So the maximal operator of the derivative is going to be to control by the hard deletable maximal operator. So that is going to be very good. And if we want to control the maximal operator of the derivative with respect to the first variable, what it happens essentially, it is that we obtain that we have to make the composition of the maximal operator with this operator here, which is the maximal Hilbert transform. And here is where the first problem appears for us. Because if we want to solve the problem in LP, this operator is going to be bounded on LP, and this operator is going to be bounded on LP, and therefore this operator is going to be bounded on LP because it is the composition of two operators that takes LP into LP. But at the end point, what is going to happen is that this operator is going to be restrictive with type, and this operator is going to be restrictive with type. And of course, if it is restrictive with type, we have a problem with the composition. Okay, so we have to manage. This is one of the technicality that we have had to solve. But the situation, as I said, the scheme and the methodology is the same. So we have a function f here, and then we need to compose with something. Now, the point is that it is not enough as before to consider the function f composed with phi, because remember that we need to control not the function b, but the gradient of the function b. And since we need to control the gradient of the function phi, we need to consider the function f composed with phi times phi prime. Okay, so if we consider this function here, what we are going to do is we are going to solve the problem here, and when we solve the problem here, we just can make the composition, and it turns out that we have to see that this is the right function. Okay, so this is the scheme that we have to solve. So the first thing is that we have to solve the Neumann problem in the upper half space for that function. Now, if we are in LP, then this function here is in LP of, this is trivial, is in LP, not of phi prime, but of phi prime to the power 1 minus p. Therefore, what we need is to control the composition of these two operators on LP of the weight. In that case, is phi prime to the power 1 over p. But this we already know, because both the maximal operator and the maximal Hilbert transform satisfy the same. They are bounded on LP from LP if and only if the weight is in AP. But now the weight is not phi prime, it's phi prime to the power 1 minus p. But that's not a big deal. So we solve the problem in the upper half space with weight, and then we need this condition. So we need the condition that phi prime to the power 1 minus p is in AP, but it turns out that this is just trivial, that this it says that phi prime has to be in AP prime. Okay. So what it is, the conclusion is that phi prime is in AP prime if and only if p prime is bigger than that p0 that we defined before, and therefore p has to be less than p prime, which is the q0 that appears in the theorem. So the q0 that appears in the theorem is nothing but the conjugate of p0. Okay, so we have solved the problem here. So we already have the u, and then we make the composition with the inverse of the function phi. And the question now is, okay, we know how to control the maximal of the gradient of u in the upper half space, and we need from here to see if we can control the maximal operator in the Lipschitz domain of the gradient of the function b. Now, to do that, what Carlos Kenny did is not use harmonic function, but analytic functions. So we have to deal both with the Poisson kernel and the conjugate kernel. So the technique is going to be working in the so-called Hardy spaces. So Hardy spaces on a Lipschitz domain is going to be a harmonic function on the Lipschitz harmonic function on the domain, so that the maximal operator has to be finite. Okay, so that's the definition. And then he needs to prove these two lemmas. Okay, well, they need more lemmas, but I have taken these two just to explain you what it is, the situation. So, for example, this one. We need to prove the following, that when we make the composition of a function with the inverse of the function phi, this is in HP of this weight, if and only if we can pass the weight to the function. Okay, so we need to have that H composed with phi minus 1 times the derivative of phi minus 1 is in HP. Or for example, this lemma is of the same kind. So we need to have that a function H is in HP of the weight if we can pass this here and divide it by that, H divided by phi prime is in HP. Okay, so for example, this lemma, this is just a remark. If instead of Hardy spaces, we just deal with LP spaces, this is trivial. This is just an immediate computation of what we need, okay? But the point is that to do that in the context of Hardy spaces is much more complicated, okay? And this is what we saw in these papers. They were stating how was the idea of how to pass from here to the other part. Okay, now we want to see what happened at the endpoint, right? So in our case, as I said, for LP, we have that behavior. This is what I said before, but now we have a second problem, because if we have a function in LP1, it is not true anymore that this function is in LP1 of the weight. Okay, so when we are working with Lorentz spaces, this is also sometimes a big problem. Okay. So the only thing that we can say is that if a function is in LP1 and the function g is this one, then g divided by phi prime is in LP1 of phi prime. What does it mean? It means thus that we don't need to solve the Neumann problem in the upper half space for the space LP01. We need to solve the Neumann problem for a different type of space, which is just this space that we have defined here. So we have defined the calligraph LP1 of omega, the set of all functions. So when we divide the function by the weight, it is in LP1 of the weight. Okay, and then what we did was to solve the Neumann problem in the half space, in the upper half space, in particular for that space X and for this space, which unfortunately is reasonable. And when we did that, we could conclude that if the derivative, if the Jacobian is in AP0R, then the Neumann problem is solvable in the calligraph space LP'01. Okay, so we have solved the first part of the theorem. So this part is okay. We already have that function, and then what happens that we need to see if it is true that if we have the control of the maximal operator in this way, that implies that this is true. And I remind you that this question in the case LP0 was solved with the technique of Hardy spaces, and this is what we try to do. And to this end, we had to define the Hardy spaces on LP infinity. Okay, so let me just say that these spaces are already in the literature. Okay, we need it, but it is not an original definition, right? I mean, there are many ways of defining Hardy spaces where the maximal operator is bound is finite over some other space which is not LP. But this is the technique that we had to develop, and in particular, for example, we had to solve the problem of the previous lemma that I have told you before, but in HP infinity. Okay, and it was not so easy. In fact, we couldn't solve it. Well, for P0 bigger than 1, we succeeded, and then this is the result. So if P0 is bigger than 1 and the Jacobian is in the restricted weak type class, then the Neumann problem is solvable in LP'01. Okay, and we have exactly the behavior of the maximal of the gradient. Okay, so this is the result. And in particular, for example, with the example that I have given to you, if we have the cone, this cone with aperture less than or equal than 1, then the Dirichlet problem and the Neumann problem are both solvable for every p between 1 and infinity. And in this other situation, the Dirichlet problem was solvable in L alpha 1, and the Neumann problem is solvable at the endpoint L alpha over alpha minus 1. And just to finish, let me just say that this theory, we have applied all this theory to the case of the so-called Schwarz-Christoffel domains, which are domains as in the figure, which is a domain that the boundary is just a polygon. And then in that case, the conformal mapping has an explicit formula, and then we are able to compute the P0, and therefore we can say where the Dirichlet problem is solvable in this kind of domains. And as I said, we have not been able to prove the solvability in L1 because we have not, we got some problems with the Hardy spaces H1 infinity, and we still are working on that. And then we haven't attacked yet the problem of the solvability of the Neumann problem in logarithmic spaces. And this is something that I hope to do with Virginia when she comes to visit us next year. Okay, and well, these are the two references, the two papers that I have been talking. One is for Dirichlet and the other one is for Neumann. And that's all that I wanted to say. So thank you very much for your attention.